So now let's look at how numerically or in terms of equations, distance or position, velocity and time are interrelated. All right. So now if you go to page, what is it? 36 of your book. All right. We can even bring it in here. All right. If you look in. All right, this box here shows the different relationships, and I recommend that you just kind of study this a little bit, meditate on it. It should make sense to you, and then the problems that you get asked on the quiz tend to derive from those different relationships, okay? So we've already talked about velocity is equal to distance over time. All right, now if we play around with this a little bit, all right, sometimes we know our velocity, sometimes we know our velocity because we're driving in a car, okay? And other times we might not. We might know just the distance we've traveled and the time we've taken to travel it, and then we can calculate the time, all right? And then sometimes we want to solve for t, okay? So be aware that you can just transform this equation by multiplying this side by t and dividing it by v, and that will give you time equals distance divided by velocity, okay? So now this is also in your book, and just always pay attention to the units. Let's pretend that distance is in meters and time is in seconds, and then velocity is going to be meters per second, but when you divide meters by meters per second, you'll notice that you're going to scratch out those meters, and the second is the denominator, and so this is going to give you seconds, all right? And that's how I like to use units. I like to use units to make sure I'm conceptually understanding the different relationships. That's why we recommend you use units in this course, all right? Another transformation, velocity is distance divided by time, that you can get here is this other relationship is velocity times time is equal to distance. And here we'll have meters per second times second will give you something in terms of meters, all right? So that's another relationship that's there on page 36, all right? And then acceleration is equal to, as we saw, the change in velocity over time. So we did this one where we did like this, v2 divided by time, okay? And then this is going to be in meters per second, and this will be in second. So acceleration is going to be in meters per second squared, like so, all right? So just as we did these transformations up here, one thing we can do with acceleration, we might know our acceleration, we might know our time, but we're interested in our change in velocity, okay? So what simple math can give us is acceleration times time is equal to, in this case, a change in velocity, all right? So this is a little multiplication symbol, and now here you have meters per second squared times seconds. That'll give you meters per second. All that adds up like so. All right, so now the last little equation that we have on here is a little bit more complicated. We have on page 36 is distance is equal to 1/2 AT squared, all right? And this is, by the way, also given, this is equation 4.1 in your lab manual, and it talks about it when we talk about the graphical relationships, all right? If you can see that this is an exponential function. It's a t squared, okay? So distance is going to increase with time at an exponential rate for a given acceleration. That's a little bit what we wanted you to understand when we were plotting these curves, right? Some of them are just linear, some of them are constant, and then the positional one is exponential. But that's because the exponential relationship between distance and time for a given acceleration just keeps pushing, and constantly increasing the velocity so that your positional changes really start to increase at a very rapid rate as you go along. This, by the way, would be time. And then this one was distance, okay? But this is for a given constant acceleration, all right? So now this one, it sort of requires the complicated math. Let's say I want to solve for time. How would I do that? If I knew my distance and I knew my acceleration, how would I solve for how much time it took me to attain, let's say, this distance here, all right? How would I do that if I knew a given acceleration? Well, you would just do some transformations like we did above on this equation. So if I want to solve and get t alone, what I do is I'll go like this. First, I'll multiply both sides by 2, get rid of that 1/2. All right, and then I have 1d. And then I'm going to divide to get rid of, get this acceleration away from t, because I'm solving for t. So I divide both sides by a, all right? And then now I have this. 2d divided by a is equal to t squared. I'm running out of space here, but what I'll do to get t, now we know time can't be negative. Time is always positive, all right? So what we're going to do is just take the square root, and we're going to choose the rational number, the positive square root. So what we do is we say the square root of 2d divided by a is equal to t, all right? So the square root of 2 times the distance traveled, and in some ways this is the cumulative distance, divided by the accelerational rate is equal to the time that it took, okay? And if we kind of look a little bit closer at this is going to be meters. This is going to be meters per second squared, and these will cancel out, and we'll take the square root of that second squared, and we'll get seconds. So that makes sense. Okay. Okay, so we just talked about how distance is equal to 1/2 a t squared, and we can use this to isolate t and calculate t for a given distance or acceleration. Remember, when you solve a problem and you have 3 variables like this, for 3 variables, and by the way, distance is going to be a variable, acceleration is going to be a variable, and time is going to be a variable. Usually you can tell they're a variable given that they're represented by letters, okay? And you're going to have given, and in this example, our given is going to be acceleration and distance, and your unknown is going to be time, okay? So usually you only have one unknown. In this class, you'll only ever have one unknown. Sometimes it helps, if you get confused by solving these, it helps to maybe make a list and figure out which ones they tell you are given. They tell you the acceleration. We're going to tell you the acceleration in this example, and we're going to tell you the distance, and then you got to figure out the unknown. So sometimes it helps, especially if you get confused by word problems, to make a little chart like this, okay? So we're just going to do example 2.3 from the book. And in this example, we have a distance of the Sears Tower in Chicago, Illinois, and that is 1,454 feet high. It's the tallest tower in the world, okay? And we're going to assume an acceleration of 32 feet per second squared, all right? And now you see there we're working in feet. We're using the U.S. system, sometimes called the standard system, the imperial system, and we're not using meters, we're using feet. But that's okay, because we got 32 feet per second, 54 feet, and then we're going to calculate t. Okay, so from before, we know that if we isolate t, we get the square root of 2 times d divided by a. All right. So when we when we deconstruct this or deconvolve it and change it all around, this is what we get. So in this case, we're just gonna plug in t is equal to the square root of 2 times 1454 feet, and that's going to be divided by 32 feet per second squared. All right, now we're going to use our units to cancel out these feet, so we're not going to be taking a square root of feet. All right, and then when we do the math in the book, basically it converts 32 feet per second squared to 16, it does this fraction, this inverse fraction, and what do we get here? We get t squared. Well, they give you t squared. If you divide 1454 divided by 16 feet per second squared, 1454 feet divided by 16 feet per second squared, you get 90.88 seconds squared, and you take the square root of both of these, and you get t is equal to 9.5 seconds. So that's how long it takes to fall this whole 1,454 feet. Okay. So then the book goes on to talk about. It actually does another calculation. So it asks you then what would be the velocity when it finally hits the ground from 1,454 feet. We know that velocity is equal to acceleration times time. All right, so this is going to be feet per second squared times second, and it's going to give you feet per second. And we know from up here, this is the acceleration. So here's a still unknown, and now this is a known, and this is our unknown. So we get 32 feet per second squared times 9.5 seconds. All right, and that will give us a velocity of about 304 feet per second. Okay, so now you might want to